Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 7, Exponential Decay. Alrighty then. Example 1 says, Malik bought a new car for 15 grand. As he drove it off the lot, his best friend, Will, told him that the car's value just dropped by 15% and that it would continue to depreciate 15% of its current value each year. If the car's value is now $12,750 according to Will, what will the value be after 15 years? Okay, so for starters, I'm not going to take Will's word for it. I'm going to take $15,000 and I'm going to multiply it by 15% or subtract 15%, so it's going to be worth 0.85. If he's right, then it's $12,750. So there you have it. He is correct. It is $12,750 as soon as he drove it off the lot. It dropped 15% to $12,750. 15% depreciation of the current car value was $1,912.50. Well, where did that come from? That would have been the 15,000 times 0.15. And that's 2,250. Oh, the current car value. Okay, number of years T passed since driving the car off the lot is 0. Car value after 0 years is $12,750. 15% depreciation of the current car value would be $12,750 times 0.8 or times 0.15. And that's where the $19,1250 came from. And you take $12,750 minus the $19,1250 and get $10,837.50. Car's value minus the 15% depreciation. That car value is now going to be equal here. So we're going to just take this value here and bring it down to the next year's car value after T years. So then I'm going to continue this. So $10,837.50 times 15% is 16,000. I'm sorry. Wait a second. 1,625.625. 1625.63. Since it's money, we're going to round to the 100th position, and that would round up to 63 cents. 1,625.63. Okay, so I take that minus that, or I could have just taken that second enter. I'll go back to what I just did and change this to 85%, which is the same as calculating 15% and then subtracting. So this would be 9,211.88 or 87 because we're subtracting the roundup of 3. 9,211 and 87 cents. That gets copied down here, so it's 9211.87. So I take that 9,211.87, multiply it by 0.15, and I get 1381.78. $1381.78 minus this. This would be a 5. I'm just going to do it manually. It's just as easy. 05. Is that right? No, it's 9. Maybe I shouldn't do it manually, huh? Now we're okay. That would borrow from the 8. Borrow 1 from the 8, make it a 7. 17 minus 8 is 9. 0. 1 minus 1 is 0. 11 minus 8 is 3. 11 minus 3 is 8, and 7,830.09. That is correct. 7,830.09. Then I take that amount. Okay, so I can go back there and do second answer. Enter. No, I don't want to do that. Never mind. 783 0.09 times 0.15. 1174.51. And the quickest way to do that is just to go back to the previous entry and change that 0.15 to 85. 85% of that value is our subtracted amount, which is 6655.58. Okay, which I got right here. Rounding, remember. So that will be copied over here. 6655.58. And I need to multiply that times, I don't want to use the rounded, so let me not use that. So 6655.58 times 0.15 equals 998.34. And then if I go back to my previous entry and just change that 15% to 85%, 85% of the value is the 100% minus 15, would be 5,657.24. Okay, copy this here. Take that value, multiply it by 0.15, and we get 848.59. And go back to the previous entry and change it to 85% to see what it would be after subtracting. Did I do that right? Nope. I hit second answer instead of second entry. So let me go back 2 entries and change this to 8. Nope. How about we just do it this way? 5627.24 times 0.85. We'll get there. 4783.15. 5627.24 times 0.85. Let me do it another way. Just checking. 5627.24 minus our 848.59 is 4778.65. I see what I did. 5657.5627. Why won't my eraser work? Hello? Alright. Try that again. Second, enter. 5657. 4,808 and 65 cents. Okay, so there it is. Buy a car for 15 grand. 5 years later, it's worth 4,800. B says, write an explicit formula for the sequence that models the value of Malik's car T years and after driving it off the lot. Okay, so we have a function notation of f of t. It's a function with respect to time, and it equals our car value after 0 years. Okay, it's not worth 15 grand after you drive it off the lot. It is only worth 85% immediately. You lose, it depreciates immediately. It's now considered a used car. You can't return it and get all your money back. So it's $12,750 is our initial value, and then we are going to take 85% of that times the number of years t to the power of t. So C says to use the formula from part B to determine the value of Malik's car 5 years after its purchase. Round your answer to the nearest penny. So that would be f of 5 equals 12,750 times 0.85 to the 5th power. So I'm going to put that in my calculator, and I'm going to say 12750 parentheses 0.85 close the parentheses to the power of 5 and hit enter, and I get 565724, which is what we had right here. Use the formula from part B to determine the value of Malik's car 7 years after its purchase. Round your answer to the nearest cent. So it'd be f of 7 equals 12,750 times 0.85 to the 7th power. And when I do that in my calculator, now I'm just going to hit second entry to return it back. I'm just going to go up here and just change that to a 7. Makes it less typing. Hit enter, and I get 4,087.36. 4087.36. Okay, so here are some exercises. It says to identify the initial value in each formula below and state whether the formula models exponential growth or exponential decay. Justify your responses. Before we begin, I want to reiterate this. Students, describe and analyze exponential decay models. This is what we're doing in this lesson. Okay, you need to recognize that in a formula that models exponential decay, the growth factor b is less than 1 or equivalent when b is greater than 1. Exponential formula with a negative exponents could also be used to model decay. So when b is greater than 1, we can use a formula with negative exponents to model decay as well. Okay, so b has to be less than 1, or if b is greater than 1, the exponent's negative. Would give us decay. Okay, so I'm going to just write a summary of that. If b is greater than 1, comma, if not I, then growth. If b is less than 1, then it's decay. Okay, pause the video, see if you can do these, and then we'll see how you did. Okay, so here we go. Initial value right here, let me do that in red. Initial value is a in the formula a times b to the x. So if I have f of x equals a times b to the x, a is the number out in front. So a equals 2 here, and b, or let's just say, yeah, b equals 2/5, and 2/5 is less than 1, therefore growth. Okay, there's no calculating here, we just have to answer the question. I'm sorry, not growth, decay. What am I thinking? 2/5 is less than 1, that is decay. My apologies there. All right, next one. What is a? A is 2. In other words, if we plugged in 0 for t, 5/3 to the 0 is 1. 1 times 2 is 2. So my initial value a is 2. B in this case is 5/3. Well, 5/3 is 1 and 2/3. 5/3 is greater than 1, therefore growth. Okay, part C. A equals 2/3. Okay, so A is 2/3, and B is equal to, yeah, I wanted to do this all in black. My pen just started working, even though I clicked on the black earlier. So A is 2/3, and B is 3, and 3 is greater than 1, therefore this is growth. All right. A is 2/3. our initial value. So if I plug 0 in here, 1/3 to the 0 is 1 times 2/3 is 1. B in this case equals 1/3. 1/3 is less than 1, therefore this is decay. Our initial value here, A, is 3/2, and B is 2/3. 2/3 is less than 1, therefore this is decay. Okay. If a person takes a given dosage D of a particular medication, then the formula F of T equals D times 0.8 to the T represents the concentration of the medication in the bloodstream T hours later. If Charlotte takes 200 milligrams of the medication at 6 a.m., how much remains in her bloodstream at 10 a.m.? Okay, so what they're saying is this is the initial value, 200 milligrams, so our time F of T would be this. F of T equals initial value 200 times 0.8 to the power of T. Well, she took the medication at 6 a.m. and they want to know how much remains in her bloodstream at 10 a.m. Well, that's 4 hours later, so we're looking for F of 4. So that would be 200 times 0.8 to the 4th power. And when I get my calculator out and I put that in, 200 parentheses 0.8 to the power of 4, then I get 81.92. So F of 4 equals 81.92 milligrams would remain in her bloodstream 4 hours later. The next part of this problem says, how long does it take for the concentration to drop below 1 milligram? Okay, well, we're going to do a guess and check process because we haven't learned how to do logarithms yet. So I'm going to use my calculator to do this. I'm going to show you a really neat way to do it in the calculator. So if you go to y equals, and you put your formula in, 200 parentheses 0.8 to the power of a variable x, and go to your window, your table set. Okay, I hit second window for table set. I want my independent variable x to be ask. So I'm going to come down here and hit enter. So change your table setup to ask, and then you hit second graph, and you plug in x values and it will tell you the y value. So you plug in 1 hour and it will tell you 160 milligrams. Our left, 2 hours, 128. 3 hours, 102.40. 3 hours, or 4 hours, we just did 3. 4 should be 81.92. Why am I hitting 8? 4 should be 81.92. Booyah! All right, and let's try 10. Okay. 10 hours, there's still 21 milligrams remaining. How long does it take for the concentration to drop below 1 milligram? Well, there's 21 milligrams remaining after 10 hours, so I'm going to keep going. How about 15? Well, 7 is more than 1. How about 20? 2 is more than 1. How about 24? All right, 0.94, but I got to check a little bit less. How about 23? And there it is. So 24 was where it got below. So 23 hours, there was still 1.18 milligrams in the bloodstream. That's not less than 1, which is what it asked, drops below 1 milligram. So when I plugged in 24 hours, it went to 0.944, which is less than 1. So I would say after 24 hours. Okay, number 3. When you breathe normally, about 12% of the air in your lungs is replaced with each breath. Write an explicit formula for the sequence that models the amount of the original air left in your lungs, given that the initial volume of air is 500 milliliters. Use your model to determine how much of the original 500 milliliter remains after 50 breaths. So we have a function with respect to time. Okay, is it time? No. Breaths. F of B for breath. F of B. We're talking about how many breaths. So our initial value is, initial volume is 500. That's our A. Times our 12%. Okay, our 12%. Why is this doing this? Our 12% air lung is replaced with each breath. That means 88% is not, so it's 0.88. To the power of N, or in this case B. We're doing F of B, breaths, to the power of how many breaths we take. Okay, so now what does it ask? Use your model to determine how much of the original 500 milliliters remains after 50 breaths. So we're looking for F of 50, which is 500 times 0.88 to the 50th power. So if I go to my calculator and go 500 parentheses 0.88 to the power of 50 and hit enter, I get 0.8377. So approximately 0.84. Approximately 0.84 milliliters. Okay, number 4 says, Ryan bought a new computer for $2,100. Hello, I changed the color, didn't I, to purple? Everybody see that? Yeah, you see that? The value of the computer decreases by 50% each year. When will the value drop below $300? So we write a formula. F of, I don't know. Here's a variable. What are we talking about here? Let's just say f of x, why not? Equals initially the computer was $2,100, and it's going to decrease by 50%, which is 0.5 to the power of x. Okay, so since b is less than 1, this is a decay. A is 2,100, which is our initial value. We want to know when this value will drop below $300. So we're going to guess and check, and we'll use our calculator. And so I'm going to go to y equals and put 2,100 times 0.5 to the power of x. And I'm going to review this again. You go to table set, which is second window, and make sure your independent variable, which is x, is ask. So when you go to second graph and you clear all these or delete them, okay, and start over. After 1 year, that computer will be worth 1,050. After 2, 525. After 3 years, it'll be 262, and there it is, below 300. So it's after 3 years. Okay, number 5. Kelly's mom takes a 400 milligram dose of aspirin. Each hour, the amount of aspirin in a person's system decreases by about 29%. How much aspirin is left in her system after 6 hours? So the first thing I'm going to do is take 100% minus the 29%, and that's going to give me 71% decrease. Each hour, 71% is remaining. The formula is going to be f of let's see, I don't know, f of a for aspirin. F of a equals initial 400 milligrams times, it's decreasing by 29%, so 71% is remaining to the power of a. So if a is 0, That would be 0.71 to the 0, which is 1 times 400 would be 400 milligrams. And after 1 hour, it'd be 71% of 400, and so on. So it says how much aspirin is left in her system after 6 hours. So I want to know how much aspirin is left after 6 hours. So I guess that should be f of t. 400 times 0.71 to the power of 6. So if I go to my calculator and go to y equals, or actually I can just do it on the home screen. I can say 400 times 0.71 to the power of 6. Enter. And that is going to equal, that is going to equal 51.24. 51.24 milligrams. Okay, number 6. According to the International Basketball Association, the FIBA, a basketball must be inflated to a pressure such that when it is dropped from a height of 1,800 millimeters, it rebounds to a height of 1,300 millimeters. Maddie decides to test the reboundability of her new basketball. She assumes that the ratio of each rebound height to the previous rebound height remains the same at 1,300 over 1,800. Let f of n be the height of the basketball after n bounces. Complete the chart below to reflect the heights Maddie expects to measure. So what's happening here is if you have a floor and you take a basketball and you drop it, it is going to go down to the floor, bounce, and come back up a certain amount, but not all the way back to the top. So now we're here. And then the next bounce is going to come up a little shorter, and it's decaying. The height is decaying until the ball bounces, and then starts to just sit on the floor and not bounce anymore. So that's what this problem is talking about. So the height of the bounce is decaying. It's getting less each bounce. Okay, so it is 1,300 over 1,800, or simply 13/18. Okay, so if that is going to happen, f of n is the height of the basketball. So f of n is going to equal our initial height of 1,800. So f of n equals 1,800 times, and it rebounds at a height of 1,300 millimeters from the height of 18. So it decreased 500 millimeters. So we're going to take that 13/18 to the power of how many times the ball bounces. So if I get my calculator out and put this formula into y equals, and it is 1,800 millimeters times 13 over 18 to the power of a variable, and I hit the table and I plug in 0, I get 1,800. Oh, that's 18,000. I have too many zeros in my equation. So I'm going to go over here and hit delete on one. I put 18,000. It's 1,800. Now when I go to my table, it's 1,800. It matches. And then I'm going to enter a 1 and hit enter, and that's 1,300. Oops. And then I'm going to enter 2, and that is 938.89, or about 939. And then I will enter 3, and it's 678.09. We'll round to 678. And then we're going to enter 4, and our table's done. And it's 489.7, which rounds up to 490. Okay. Next page says, A, write the explicit formula for the sequence that models the height of Maddie's basketball after a number of bounces. We've already done that. And it is right here. Okay, so there we have it. F of n equals 1,800 times 13/18 to the power of n, where n is the number of bounces. Now it says to plot the points from the table, connect the points with a smooth curve, and then use the curve to estimate the bounce number at which the rebound height drops below 200 millimeters. Okay, so I copied the table over so we don't have to keep going back and forth, and we're going to plot points. Let me graph this in green. So, 0 bounces, the ball is at 1,800 millimeters height. After it bounces one time, it comes back up to 1,300, which is halfway between 1,200 and 1,400. And then bounce 2 is 939, which I would say that's 900, so it's a little bit higher than halfway. So 900 would be here, so 39 would be a little bit higher. Okay, and then 3 is 678, so 3 I'd go up to 6. This is 7, so it's a little below, so I'd say about right there. And then finally 4 is 490, which is not quite halfway to 500, like so. And then it says, connect the points with a smooth curve and then use the curve to estimate the bounce number at which the rebound height drops below 200. So this is difficult for me with this pad, so I'll try. So this is coming down, and I'm thinking it's just going to keep going at a steady rate like so. All right, so when it drops below 200, I would say it would be around 7. That is my estimate. Okay, it says to estimate. So before we finish this up, though, let's check, see if we're accurate, for our accuracy. So after 5 bounces, was it below 200? The answer is no. 5 bounces was 300 something, so my approximation is fairly close. And after 6 bounces, we dropped to 255, and I was around 200, so I'm a little low there. And then on the next one, 7, it is 184, and sure enough, my estimate was actually the right answer. After 7 bounces, it did not come back up to the 200 level. Okay, that is the end of Lesson 7. Review the lesson summary and go to your problem.